Okay, in this video, we're going to try and find out the mass of a helicopter by using the concepts of momentum. Now here is the helicopter in question. It's just a toy helicopter, something very small, but it can illustrate the ideas of momentum really well. So let's go through a bit of theory first, and then we'll do the practical. So, if this is my helicopter here, we know that it has a weight, mg, and the way that it hovers is that it's throwing air down, which in turn creates upthrust. When it's hovering, these forces are identical, and that force that's being driven up is what we're trying to calculate. So how do we go about that? Well, we use Newton's second law of motion, and though many of you think it's F equals ma, in actual fact, in its first instance, how we wrote it down in Principia, it was the rate of change of momentum with respect to time. So it means how much momentum change is taking place per second, could be another way of looking at it. The momentum change per second, I'll write it per second, I'm using a unit rather than the symbol, so it's a bit confusing, but trying to illustrate that we'll use it per second rather than any time period per second, which of course is equal to the mass times the change in velocity per second. So I suppose what we really need to work out then is how the velocity of the air being thrown down and how much mass is moving each second. So let's take a look at this instance. Let's imagine that this helicopter, therefore, with the propeller, is driving down the column of air, and that column of air is going to be a nice cylinder shape. Now, we're approximating there. Of course, this is more like chopping the air down, but let's imagine it's a cylinder that's being driven down. We have a radius, which is the same as the copter blade length, and we have a length. And that gives us a volume of air. Remember, we're trying to work out the mass of air. So therefore, the mass is going to be the density times the volume. The density of air, we know, it's 1.3 kilograms per meter cubed. So we have the density. Now, what's the volume? The volume is going to be the area multiplied by the length. And just to put more flesh on that, the area is pi r squared by the length. Excellent. Now, what I've said here is, I've said I'm looking for the rate of change of momentum per second, or indeed the change in mass per second multiplied by the change in velocity. So the mass per second. So, which is an easy assumption to make. So if I'm looking at the mass per second, and I keep dividing that per second, then I could rewrite this as density pi r squared, the length per second. And the length per second is in effect saying that is a definition for the velocity. The number of meters per second would be the velocity. So in effect I have pi r squared v. It's an expression for my mass per second. Good, let's work that back then. Let's take this expression and plug it into there. So the force is now rho pi r squared v, change in v. And once again, another big assumption I'm going to make is I'm going to make the assumption that the air particles above are sitting at zero speed, and when they're thrown through, they gain a velocity of v. We could have a long debate about that, if that's the case. We could say, oh, well, surely it's an average speed, etc., but let's just keep it quite simplistic with a very complicated system, and let's just assume that that is actually the change in velocity is v, therefore making this equal to rho pi r squared v squared. And finally, of course, the force, which is in this case is the weight, because they must be balanced, is mg. Therefore, m, if I divide through by g, is rho pi r squared v squared over g. a bit of a complicated equation, but nothing which you couldn't have worked out from first principles. So let's take a few values then. We're looking at density we have. We need to work out the radius. The radius of these blades here are approximately, you'll see from tip to axis, 10 centimeters, or 0.1 meters. We have a velocity, which we're about to obtain, and g is obviously, let's say, 10, just to make life easy. Okay, let me show you how we're going to do the velocity. We're going to use this wind speed meter, and in reality, what needs to happen with the wind speed meter is this thing doesn't fly very stably until it's in the middle of a laboratory, as I'll show you now. But what you would do is you would fly this and then go in search of it with the wind speed meter and stick it underneath the blades. But I'll just show you. It's fairly stable once it's established its flight. There we go. Or not quite. And it starts to hover and heads off. So what we're going to do is, in order to make this easier and keep it on the video, I will hold this over there and look at what sort of speed the air is being thrown through the meter. If I place it over the top, it's not going to catch all of the air, it will drop. So we need to get an average speed of it through the meter with it hovering. So we're looking about there is about 12 kilometers per hour. So in reality, let it float in the room and then chase it with the wind speed meter. 12 kilometers per hour. So the velocity is 12 kilometers per hour, which is the same as saying 12 by 1,000 if I'm changing it to meters per second, and that gives me 3.3 meters per second. Okay, so now I've got all the details I need. So the mass is going to be density of air by 3.142 pi by 0.1 squared by 3.3 squared divided by 10 gives me approximately 0.04 kilograms or 40 grams. Brilliant. Let's just see what happens. If I bring in a set of a balance, bingo. Pretty much exactly what we said. Okay, hope that makes sense.